Okay, I've taken care of the busy work, gotten that out of the way. See when Nathaniel. Alex, welcome. Thank you very much for coming today to join us.
Hey, thank you. Thanks for the invitation.
Sure. Wait for Dr. Purcell. Give him a few minutes. He may be changing a diaper or something like that. Who knows? Mary Lou, how was your 4th of July?
Oh, it was really, really super. Montclair has a really good parade with lots and lots of fire engines, which is exciting. And one of them I thought was funny, from a town not far away called Little Falls. Behind the fire engine, they had a very nice long boat, and it was called Fireboat Number 1.
It was going down the road. Is that right?
I don't know if there's a number 2, but there it was. And they had lots of marching bands and people with bagpipes and people in fancy costumes dancing. And then we had really good fireworks. So it was a good 4th of July. It's a great, great thing to experience.
I think I missed something. You mentioned bagpipes.
Do you like them, David?
Oh, of course. I host a tent for my clan.
You play the bagpipes?
I do not. I play fiddle.
Oh, that's much better. Yes, there you go. Yeah.
A little more socially acceptable. Usually.
Yes, well, I'll tell you a joke about bagpipes sometime in private. There you go.
All right.
Hey, Nathaniel.
Hi, Mary Lou. How are you?
Very busy. How you doing?
Very busy as well.
Yes, I know that. Yes.
Hi, Alex. Thanks for coming today.
Yeah, hi, Alex. Good to see you.
Where are you located, Alex?
I'm in Washington, D.C.
Bet it's hot down there, huh?
Yep. It's close to 100 Fahrenheit, I think.
Yes, so it is in Newark as well.
Yeah.
All right, it's 4:02 p.m., so let's kick off the meeting. I see Nathaniel's claimed host, which is great. I've already started the recording to the cloud, so we're good there. Welcome, everyone, to the Thursday, July 11th HamSCIence Zoom telecast. Today, we've got a first of what we hope will be at least 3 or 4 speakers on the subject of sporadic E. It's great that somebody, maybe it was Kuldeep, suggested the topic some time back. And we've had a lot of help from Gareth and others lining up speakers and whatnot. So without further ado, unless there's anything that's really urgent and imminent, we'll turn it over to Alex and let him begin today.
Okay, yeah, thanks a lot. Yeah, this is a talk based on a paper that I published a couple of years ago. So hopefully it's due to most of you. But the subject is this automatic information system signals, which are 162 megahertz signals used primarily for shipping information. We got a question from a different part of the applied physics lab where they were seeing these signals pop up from chips from thousands of kilometers away, and they had got rid of all the usual suspects, such as corrupted messages or other things such as tropospheric ducting, which is known to lead to long distance propagation sometimes. And they still couldn't figure out why they were coming in from so far away. And so they asked, could it be the ionosphere? And I thought probably not, because 162 megahertz seemed very high to me. But then when we looked into it, I looked at ionoson data in the neighborhood, and sure enough, there were sporadic events. Oh, sorry.
Did you hit me today?
What's up? Oh, sorry. Is there a question? No. Okay. Well, oh, okay. Yeah. So we'll go through just a little bit more information on what AIS is. We'll kind of talk about some of these collections that where we saw the long distance propagation, and I'll show you the data that makes me think that it's the ionosphere that is causing the long distance propagation. So this is a map of ships that basically anything over 100 tons has to have one of these transmitters on, and telling its neighbors, what its name is and where it's going and so on. The commercial system uses 12.5 watts. There's an kind of a private use one that can be a little bit lower power. They put these transmitters on buoys and bridges and all sorts of things to help others know where they are and avoid crashing into each other. In theory, they operate as a line of sight system, so that that you don't get too many messages arriving from all over the place and clogging up the network. But in practice, there are occasions when signals come in from much further than line of sight. So there are several companies that monitor these things. So Spire is one. This is their map of a month of these locations, and the colors indicate how they were observed. They have satellites out monitoring them, and so that's the yellow. But the green are received from land, and the magenta are received from the sea. And you can kind of see, that's the only thing that's on this graph is the transmitter locations, and you can obviously see that the world's land masses and even the rivers are pretty well mapped out by these transmitters. So there's really a huge number of them out there. In our case, we're only using a database of receivers that are located in the eastern United States and in Puerto Rico by the Coast Guard that's monitoring these. And even just in those sort of 10 or so receivers, there are almost 30 million links received in 3 days. And what we see is, so this is like a log histogram. So you see, millions of links at short distances, and then it drops off rapidly as you get out to about 1,000 kilometers. There's this kind of gap, and then you get this other population that we saw about 6,000, I think, or 6,692 links that are over 1,000 kilometers in great circle distance. So we don't have time of flight, unfortunately. So we don't know actually the distance that the signal traveled, but from one point on the surface to another, it was 1,000 kilometers or more in those cases. And if we look at the time series, given that we're in the eastern US and it's summertime, I took Bar Harbor as the nighttime. So that's the black crosshatched region. Is nighttime in Bar Harbor in Maine. And so you can see almost all of them come through in the daytime, and almost all in the first 2 days of the 3 that we had to analyze. So that's kind of the first clue that it would be an ionospheric phenomenon, rather than something else. Although of course there are other things that occur only during the day, but the most intense sporadic heat should be during the day, I think. So then when we looked at we calculated the strength of tropospheric ducts on the eastern US, and essentially it's kind of hard to prove a negative, but we looked through and we couldn't see any relationship between where we were seeing tropospheric ducts and where we were seeing this long distance propagation. However, when we looked at the 3 ionosons on the East Coast, Millstone Hill in Massachusetts, Wallops in Virginia, and Ramey in Puerto Rico, we saw that on the first 2 days they saw the highest intensity of sporadic E that they could see. So the maximum frequency of the ionosons was reached, and on the 3rd day it was not, and also at night it was not reached. So if you look at a specific example, you got this clump of signals coming through from the AIS. So you can sort of see where the ship transmitters might be in the Great Lakes and in the ocean, and some receivers on the coast. And at the same time, in approximately here, I suppose Millstone Hill must be about there. We see this blanketing sporadic E layer going off the scale. So the system only ran to 10 megahertz, but it's clearly going at in excess of 10 megahertz there. And so to kind of try to visualize when and where this is happening, I've put these dots where the size of the dot is the intensity of sporadic E that's being observed. And then when it gets to the maximum, it goes white. And hopefully you can see that there's an association here between where most of the links occur and where the sporadic E is most intense. So yeah, you can see there Arabian is saturating, and now Wallops is going. And then on the second day, which is coming around now, we're going to see kind of the same thing. We got intense sporadic E up there, and the links. And so now we're coming through to the third day, and what you'll see is that there's not actually as much sporadic E, and then also not really the same kind of link. So none of them actually go white. In other words, none of them reach the maximum there. So that's kind of the the best way I can sort of visualize the association that we're seeing. I'd really like to get my hands on more of this data or similar data to be able to confirm it. But if we consider what's actually happening here, we to get a sporadic E layer, what we know is that you need to have a compressive Lorentz force so that the plasma is squeezed together, and so the density is increased at a location, but maybe the column density might not change. It just all gets squashed into a pancake. And we think most commonly the zonal wind shear actually is what causes that force. So when you have a wind blowing east below the layer and west above the layer, it can drive an electric field that compresses the plasma into a pancake. And the same thing can happen in the north-south direction, but from the ICON satellite, Yamazaki and all, in 2022 showed that the zonal wind shear is the most effective in terms of associations with sporadic heat. So yeah, that's kind of the theory of what's happening. And so what I would be arguing is that just very occasionally you get a particularly strong wind shear and maybe more metallic ions than we typically have. So you need metallic ions because they last a lot longer than the typical ions that you get up in the atmosphere, in the upper atmosphere. So if you get a combination of those two things, you might get to much higher densities of sporadic E than what we typically see. So this layer would be, which is a rocket observation, is at least an order of magnitude less dense than what we would need. But we think every now and again it could get much more dense. So just kind of from a first order geometry calculation, assuming the layers are 100 kilometers and taking a 1200 kilometer path as kind of a reference, we would need a 10 to the 13th electron per meter cubed sporadic E layer, which is an order of magnitude more than what you would see in the models, and it would correspond to a vertical ionogram that goes all the way across to 28 megahertz or so. So that's really very high. But there are a couple of cases where we've seen similar, or like this one from Japan is going up to about 25 megahertz in the vertical. And there was also a case in India, which which was reported in the 70s, where they also got above 20 megahertz. So I think it could be reflection, but I don't know. It's also possible that the signal is somehow scattering rather than reflecting in the normal way. So it's not clear exactly what the propagation mechanism is, but I think it is linked to sporadic E in one way or another. So yeah, just in summary, we've found this relationship between greater than 1,000 kilometer great circle propagation of AIS data links to intense ionospheric sporadic E layers. And this tells us that it's possible that those layers get to be 10 times more dense than what was expected by, I guess, the ionospheric community, at least the US ionospheric community. The fact that these signals are mandated for use in all large ships means that potentially we could use them to monitor sporadic E and the underlying drivers of sporadic E across the world, if we could somehow get hold of enough data to do that from receiver networks. So I also have a couple of recommendations related to this for HamSCI. So that it doesn't have to be AIS. It could be any signal in that range, maybe above 100 megahertz or so. The nice thing about that range of frequencies is that it's a little bit easier to know what's happening, as far as it's kind of guaranteed to be single hop when you get out to those distances, you can make kind of straight line propagation assumptions, I think, with more fidelity than you can with say HF band signals. So I saw the DX maps. They have a sporadic E mapping tool actually, which is pretty cool. They have a lot of coincidences with what I'm seeing in the AIS data actually. But maybe we can build on that somehow to get more sporadic E observations from citizen science observations. And then the second thing would be just if we could get time of flight, that would make things a lot easier as far as for not just for this band, but for all different bands. If we can somehow record the time of flight between transmitter and receiver, that would be a great help. And then finally, just try to be somehow systematically tell whether it's whether the propagation is through this mode or that mode would be very valuable. I have kind of a bonus slide based on the recent eclipse. So this is actually 160 meters, and I was just it was kind of cool to find in the WhisperNet data that we basically the eclipse makes a hole in the what normally there would be too much absorption to get much propagation at 160 meters during the day, but just along the path of totality there was this channel that kind of opened up. So I thought that was pretty cool. But yeah, thanks. I'm happy to take any questions.
Yeah, that's cool, Alex. We did see that same hole open up in our AM broadcast Doppler data. And 160 meters just above the AM band.
Yeah, it's kind of nice that's another area where with the low power you get kind of a reliable. There's only really can be that, it's like it always should propagate, but it just tells you that there's not so much absorption when you see it coming through. So yeah.
Alex, I had a question. So you were showing that some of that a couple of cases of Ionoson data showing sporadic E up to 25 megahertz. Like, I'm surprised to see that it's not a common observation. So is it something that we should be looking at, or our Ionoson operators should be looking at? Or I realize I'm not even familiar with the operation with the Ionosons, if they actually sweep up to that kind of high frequency or that part of the HF band.
Yeah, so they're in typically it's not a hardware limitation, I think. But typically if you're running an Ionoson like at this point it was let me see. So 2021, they were still in the sort of minimum operations where you've got to spend like they try to make the system operate efficiently, which means if you're not going to see anything further up, or if you assume that you won't see anything, then you wouldn't waste a lot of time scanning all the way through it all the time. So when you have a phenomenon like this one, which maybe happens a few days a year at most, then they're just not going to run it. And so that allows them to get a higher cadence and maybe more power into the areas of the frequency band that they're more interested in. It's an interesting question. I mean, what I would love to do is to have like, because you kind of see it track across like even from the limited data set that we have, you can see that the phenomenon is moving across the way. If we could somehow link up some oblique observations like this, and then say at Wallops have the Viper system, just send a rocket into it or something like that. Or likewise, I mean, if you're on the West Coast, you could maybe have a better chance of seeing it come across. But it's something that they're probably not going to do. They're not going to change their routine operating mode because it would make them worse at the main thing that they're doing. But
yeah, for Viper, we were only looking up to 5 megahertz
Okay.
from VLF up to 5 megahertz.
Okay.
Yeah, it's like that's kind of the problem is.
But that doesn't mean we can't have
something
a rocket mission that goes above that. Ionis funds generally will stop at like 10 to 12 megahertz because that's where the propagation is in near vertical incidence. It's very rare that they go even up to 30 megahertz, but clearly it'd be nice to have some kind of scanning system that goes like just below 30 up through even UHF. I mean, we can get sporadic E propagation at the 70 centimeter band, 450 megahertz at times. That's rare. Fairly common is at 2 meters, which is 150 megahertz, close to this 162. And it's quite common, it's at 6 meters, 50 megahertz. In fact, I was informed that there was an opening to Europe today on 6 meters. But it's certainly under studied, this phenomenon. One of the things that would be nice is more whisper transmitters in these frequency ranges.
Whisper, or I guess what's the other one? PSK Reporter. I know they have some. They have some more operators in that band.
Yeah, Whisper is a continuous mode where it's a beacon, whereas PSK Reporter and the systems that will like pick up FT8 transmissions, those are people actually trying to make contacts. So you're going to have a dearth of information when people think that there's no propagation.
Yeah, so the nice thing in that regard about AIS is that it's kind of on all the time,
right,
as well. So
it's kind of interesting. It's the same. Their same situation is their situation similar to that with CB radio, where CB just shy of 30 megahertz was put there thinking that it would not propagate long distances and it'd be line of sight. Well, of course, we know that's different. That's not true. You can hear California from the East Coast fairly often in those frequencies.
Can I just sort of chip in?
Yeah.
The reason you don't see 2 meter sporadic E or this 162, by the way, this is the highest frequency in a peer-reviewed paper reported.
It is? Okay.
An extensive search for my thesis. I've got your paper recorded in it.
Oh,
And
thank you.
this is it. Although there are plenty of reports, as was just said, at 2 meters. But the point is that the reflecting areas at 2 meters that are strong enough to reflect at 2 meters are very small. They might be hundreds of meters or a kilometer in size, and they move around, which is why 2 meter signals can be even worse than on, say, 6 meters, where signals can come and disappear in fractions in seconds. They're 5 a night. They're really, really strong and then gone. And the chance of that occurring, happening to be over the top of an ionosonde, is pretty damn small. And the footprint of the ionosonde on the ionosphere is pretty big. You know, it's illuminating maybe 100 kilometers in a circle. So to expect these tiny reflecting areas, which could be very intense because sporadic key layers are not uniform, they're thicker and thinner as you go across them. And when you think that the shape of the blob may also, there's evidence that sporadic key blobs can be funny shapes, like concave at the bottom. So you've got a mirror, a mirror that will magnify the intensity. The chance of that being over the top of your ionosonde is low, and I found that at 6 meters. It's bad enough at 6 meters. To try doing it at this frequency. And I would turn it the other way around. I think what you've got here is a way of studying very intense sporadic key, which simply no other techniques will do. The time coverage, the spatial coverage just isn't good enough with any of the other instruments.
There are two
Yeah,
things
well,
I'll add to that.
also-
One is that there is a propagation mode that does extend up into the microwave that's quite common, but very short-lived, and that's meteor scatter. And you need to select out the meteor scatter signals. The other thing is that I have seen sporadic E at 1296 because I've been at the Sonderstrom ISR when they were looking at sporadic E layers at that frequency.
Yeah, I think Inca and scatter. That would be a different propagation mode, I suppose. That I mean for example, also the RSC at 430 megahertz. That's also. But that's it's kind of a it's not a reflection. Then it would be Thomson scatter instead. But so thanks a lot for the comments, Chris. I also saw your paper actually in the I think kind of a similar vein, and I do agree that as a monitoring system, it's somewhat rare, or there's some unique value to this this kind of oblique like distributed sensing. I wish I had you as a peer reviewer for the proposal to buy more of this data, but they didn't want to do it. So so I'm trying to figure out how to get more of it. But I think the amateur networks might be useful. The one problem with the public AIS, because there are many public databases of where the transmitters are for AIS, but typically the receive location is not stored, and that's been the limiting factor in the public data sets that I've seen.
Alex, you suggested that we have it would be helpful to have more whisper data from the amateur community. What frequencies were you thinking? 6 meters or higher than that, or what?
I think you got to go higher, because when you get a oblique, it's as your angle of incidence comes closer to horizontal, it becomes easier to, at 6 meters, I think you could quite easily have F mode propagation. And for me, if I'm looking for sporadic E only, that's a contaminating, that's a confounding factor. Basically, I'm struggling to differentiate between them all of a sudden. So if you get me time of flight, however, then 6 meters will be fine. Then we can tell if it's coming off of 100 kilometer layer or 200 or multi-hop and all that. It would be much easier to deal with all of this stuff if we had time of flight. down to like, I don't know, a microsecond or something. But if you had GPS timing, you could, which most people do, it would be easy to get that, I think. Well, maybe not easy, but it'd be possible.
Someone correct me if I'm wrong, but I believe that it's extremely rare to get F mode propagation at 6 meters.
At solar maximum, it happens.
yeah.
But the skip distance would never be as short as 1,000 kilometers. It would
Right.
always be 3,000,
That's
4,000.
almost always for sporadic E or ducting
Well,
proceed.
Yeah, 1,000 kilometers, but 1,000 kilometers is that's the shortest path here. So I mean, we there's no reason we want to restrict ourselves to 1,000 kilometers either. I mean, we could.
But your typical would be around 1,500, wouldn't it? Between 1,000 and 2,000 is the sort of typical.
Yeah, but yeah, as I say, time of flight would just be great for the if we could have that from Whisper.
I must admit, it's really interesting to see this analysis adding in some extra input of data, because one of the problems amateurs have in our aspect of studying it is that we run out of people when you get too far south in latitude in Europe. So although there might be some really strong sporadic E quite well south, we've got nobody at the other end to receive it. So we wouldn't know much about it. So this is really useful for down the west coast of Africa. But one of the things I was going to mention was how often I notice in the work that I do in the amateur side of it is how common you get multi-hop paths, and that your graph of the distances would probably, if you extended it, have maybe 2 or even 3 peaks for priorities of 2-3 hop sporadic E paths, showing this one here. Yeah, so you might well have a median distance of, I don't know, about 1,800 K for the first single hop ones, and the signal strength would be very strong. But then you get this real drop off in signal strength for the multi-hop paths. But they're surprisingly common. In fact, we heard today they were reported quite widely. The other thing
on 6 meters, Jim, yes, but on 2 meters, no.
2 meters, no, not so much. It's mostly single hop. But I did have a look at some upper air charts for the dates you mentioned in your piece, Alex, which if you want, I can either send them to you or show them to you by sharing a screen.
Yeah, whatever you want. I mean, that sounds interesting. We didn't see anything. This is that's the long. Okay, there is actually one like that was at like 5,000 kilometers, but it turned out to be a corrupted message anyway. So there were no additional peaks in this data set. Can just say that maybe down to power, 12.5 watts, and yeah, I think it gets harder and harder to get multi-hop, but as Chris was suggesting.
That's exactly the shape you'd expect from single hop sporadic E, though.
Yeah.
Tailing off to 2,500 is about right.
Yeah. Okay. If with your permission, I'll just have a little look and share the screen. Okay, I'm going to check. Can anybody see this?
Not yet.
Try it again. Alex said down share.
Okay, let's just come up here. Be with you in a second. So sharing again. Share screen. There we go. Anything coming through? Yep. Okay. Well, what I did, I had a look at some of the early images from your paper, and it's absolutely fascinating how there's this parallel with the amateur world that we tend to also notice. A local solar time morning peak and a afternoon evening peak. And then I thought, well, at Puerto Rico, you've got this kind of broader peak, and I think there is something to do with how the tidal winds in the E region affect the background capability of it to make E's. Is that something which I'm talking out the back of my head on? Because I think the response to the semi-diurnal solar tide is tending to dominate with mid-latitude events. And then as you get down towards the equator, the response is not so strong, and the diurnal tide is perhaps more significant. So you tend to get a more broad peak in the middle of the day. So that was one thing that wanted to comment on. And then the other thing, which may or may not be helpful, a lot of stuff I've been doing has been relating to why sporadicy in the amateur world is obviously very sporadic in time, but particularly in geographical location. And some of the aspects of that suggest a link with atmospheric gravity wave propagation from weather events. So I looked at some of those. And one of the things over many years now I've been looking at with upper air data is basically turbulence in association with jet streams, but also vorticity, which is the brown shading, orange shading on this graph. This is for the 13th, when you were looking at paths in this region, I think, Alex. Was that the 13th one down in the...
Yeah, I think that was the first day where you had a Raimi in Puerto Rico, as you said, that there was all day there.
Okay, well, this one, I was actually wondering, that had a lot of signature to me about I was not sure whether it was all sporadic E, and I was wondering what we do in this sort of world when there might be a combination of sporadic E and tropo going on, because the way it was spread and shared around kind of felt a bit more tropo-ish. But anyway, looking at the pattern here, there's an upper ridge which tends to be associated with a lot of sporadic E events, not so many as jet streams, but you'll notice the vorticity, little vorticity maxima here that move through the pattern in that day, but none of them look very strong. And when you look at the, I looked at the Raimi ionoson data, you've got the pale blue is 10 meters and the lime green is 6 meter events. And you can see there are these little rather randomly distributed periods when 6 meters opens up. But this is something I don't usually see with Europeanese, this widespread variation in height. Normally when you get an ease opening developing, it tends to converge on a fairly narrow height range. This appeared to be quite randomized compared to the usual expectation. It's perhaps more clear in this one. But when we go to the next, I won't dwell on this because I discovered I haven't got any weather data. Normally I do a weather data, but this is the one for the northeastern states. And this is an upper air chart at 300 millibars or hectopascals as they are now. And there's a tiny little minor upper trough feature here going across the northeastern states. And the real vorticity maxima, just about where you were getting the paths crossing of that opening. Now, sometimes these things turn out to be significant, and sometimes over many years now looking at them, they don't. And the ones that do tend to be the ones that have quite a high rate of translation geographically. So this one, you'll see, really nips along. So, and then you've got vorticity ribbon on a cold front coming in behind it. But this whoops, let's go back to that little hotspot there. Now, whether that was the hotspot or whether it wasn't, but it fits in with openings that have happened in the past, that it takes surprisingly small scale features sometimes to do it. And yet other days, those same small scale features have nothing to do with ease at all. They just don't get involved. So maybe there's global things like change in the K index, the stability of the magnetic field, or there might be just pure delivery of the raw material, whether there's enough meteor debris up there. But anyway, I thought that might be of interest. And then when you plot the here's the equivalent ionoson plot for Millstone Hill for that one. And you can see there are some quite strong peaks in here, but again, not much focusing on the single height. And when I do my next visit, I'll bring along some of a UK or European style opening where there is very much a common tendency for everything to focus on virtually a single height, where it just converges usually at about 100 kilometers. Anyway, there we are, for what it's worth.
Okay, thanks. Yeah, that's interesting. So I suppose my first comment would be that with just the 3 days of data, I'm hesitant to draw like too many conclusions about some of the finer details. But I think that the question of we know that tropospheric ducting does also allow this kind of it might look the same to the analysis that I did. It's possible that tropoducting could sneak in there in principle. In our case, we looked for that and didn't find. We calculated the duct strength. I think it comes in at M units, but so we did consider whether that could be the case. Could be the cause. So I think in terms of a direct, like whether the signal could have gone through the troposphere, I would say I don't think so in the signals that we had. But that doesn't mean that the phenomena are uncorrelated. So if you do have gravity, you can have gravity waves going all the way up to the ionosphere and contributing to sporadic E. So it is possible that as you said, there could be an association there some of the time, or that that feature that you showed going across there could actually be the cause of what we saw. But it would have to be I think an indirect mechanism where it creates a wave that goes up into the atmosphere or further up into the atmosphere and does that, or contributes to the wind shear.
Yeah, exactly.
So I think I suppose just taking a step back.
I was going to say, when you mentioned you measured the duct details for the tropoducting, what height intervals did the model data come in from the data set you looked at for that, Alex, just as a matter of interest?
So
because it
my
could be a
colleague Tom
very,
had
very strong surface duct, the ocean surface, which is below the first model level in some of these archive models. So I'm quite interested to know what the archive lowest model level was.
So my colleague Tom actually did that part of the analysis, but I'd be a lot surprised if we didn't say what it was in the paper. Or maybe if it's not in there, I can look up. I think I have the file here. But yeah, where's the oh, so it was the ECMWF era 5 data that we used.
Okay.
So that Tom used, I should say. So what is the resolution? 137 level. I think that's like a standard product.
Yeah, I think some of these modern models, like that particular set, have a concentration of model levels right down near the surface where it wants higher resolution, and also in the tropopause near the jet stream, and slightly more spaced in the middle. But I'd have to look up to see what those levels were low down. But it'd be interesting, because it may well be it didn't really capture in that data set the value of a very surface-based ocean duct.
Well, yeah, so it's from these 137 levels are from the surface up to a height of 80 kilometers, it says. So the pressure levels are presumably in hectopascals, like 1,975, 950, 925, 900,
right,
and so on. So
yeah, no, that should be good enough. Yeah. Okay.
Yeah. So, but in any case, I think really what I would like is that I think that the tropospheric reanalysis data is pretty good, especially compared to the ionospheric data such as it is. So I think if we get enough statistics about the occurrence of this phenomenon, it should be possible to see like when it is tropospheric ducting and when it is not. So as long as those are the only two major sources of of this phenomenon, we should be able to find the sporadic E pretty uniquely, because as I say, the meteorological reanalysis data now is really pretty good, for at least good enough to do statistics. And yeah, my colleague Tom had said, he told me that they would see this kind of thing only if you have a hot, dusty air blowing out over the ocean. So basically, if it's tropical, maybe off the coast of Sahara, like off of East Africa, you could expect that. But that's kind of the only place that he would, or one of the only places where he would think that could happen. I want to say also, like, there are big problems with jamming. Some parts of the world you couldn't do this because there's like a war happening and people are messing with the AIS for that reason. So, but those are also kind of localized.
Alex, you had something for the HamSCI on your last slide. Can you go to these?
Yeah.
And elaborate a bit more on it?
Sure.
The last one.
Yeah, let me see if I can. Okay, I probably can't make it full screen now, but if you can see that, then we can go. Is that visible?
Yeah, it is visible.
Yeah, so yeah, I want to highlight this, the DX maps, because they have something like this. I think it's 144 megahertz is the highest frequency that they use, but they have these kind of nice sporadic E maps. I couldn't get to the underlying data, and I also couldn't find out how I think they're just like user reported, this is sporadic E or this is something else, and I actually believe that, well, I didn't initially believe this, but now that I've investigated a little bit, I think they really can tell. Like, I'm not disputing that people can tell the difference between the different modes, but for a peer-reviewed or for a scientific thing, it's kind of, you don't really want to have people just guessing what's what, or like it would be much nicer to have a more systematic way of saying what's what. But yeah, so in any case, I believe what they show is true and real, but I can't use it at the moment because I can't get to the data, and because it's developed in a way that's not that easy to reproduce.
Alex, you can download the data behind it from.
How do I get there?
DX maps, or maybe
it's on DX maps, right?
Take that offline if you like.
Yeah.
I got a chunk of my data from. I mean, I wasn't using 2 meter data, but I got a chunk of my data from DX maps, and it pulls together multiple sources of reports. It's very good.
Okay. Yeah, okay, that's great. Yeah, I would like to use that. But yeah, maybe the hams are interested in starting to log AIS reports as well. I mean, that seems like it could be a protocol that we could implement, and that you have tons of transmitters that will always be switched on. So they say where they're coming from as well. So that's kind of an idea that maybe HamSCI could use that AIS as a signal of opportunity.
You mean to receive it on our systems?
Yeah, like, could it be built into Whisper or something, or I don't know how that would work.
Well, here's what I'll point out is that the A to D converters that we're making use of do have the capability of subsampling at those frequencies. You sample at a lower rate, but you feed it the frequency and it'll basically alias it down. So it is possible for our receivers to do that if we put the proper front end on it.
Okay, I think that would be really valuable, and you start to get information about what's happening over the oceans, as well as over land. So I think that would be great. Yeah, I mean, you can buy an AIS receiver for a couple of $100. I guess it wouldn't take that much to figure out what it's doing internally. But yeah, the second thing is just the time of flight. I just really want to emphasize that in all frequency ranges, this would make our lives a lot easier. if we had that information.
Does the
along with
AIS signal have timing in it?
Not that I'm aware of.
Okay.
But I was thinking for Whisper, you might be able to do it.
Yeah, I know that the Whisper modes are being worked on that will have timing information.
Okay. And yeah, the third one, I guess it alludes to the issue that when I read into what was happening at DX Maps, it seems that people were like it's sort of user attributed, which is probably does work, but it would just be nice for us to have a systematic kind of uniform way of doing it to avoid user error. And yeah, like I said, also another aspect of that is that if we just look at the links, and I mean, we can do tropoducting maps, but it's not actually that hard to figure out where the ducts are in the troposphere. So we should be able to take out some of these confounding factors without too much effort.
Well, that was an excellent presentation, Alex, and obviously generated a lot of good discussion. I think more importantly, further food for thought too. I think the recommendations for HamSCI are welcome, and certainly presented in the proper form.
Okay, thank you very much for the invitation. I enjoyed talking to all of you and hearing your input and so on. So yeah, I guess good luck with the project, and yeah, look forward to seeing what comes out of it in the future.
Yeah, the challenge is in some ways we've got many projects going on, which is good. In fact, I was just sitting here thinking, I heard Jim mention about a comment about stability of magnetic fields. And I believe our next deployment of scientific instruments through HamSCI, hopefully next year, will include not only HF, but VLF and also magnetometer data. So whoever came up with that idea or is promoting that, kudos to them, because it sounds like a number of us are thinking that same direction. So that'll be exciting to see.
Okay, great.
The good news is that we will, over the next few weeks or perhaps into early August, be hearing from both Jim Bacon and Chris Deacon. So we'll have more of their insights and whatnot. So that's very welcome. To look forward to that in the next couple of weeks. Any other comments or questions? We're getting here close to 5 o'clock from the rest of the group.
I just echo my thanks to Alex for your presentation. And we also appreciate the paper that you published last year on validating SAMI 3 and using Whisper observations. So thank you very much.
Sure. Okay.
Great, thank you again. Is there anything else that we want to discuss or bring up this week? Otherwise, we'll start making preparations for next week and see everyone again next Thursday afternoon. All right, if it's good, we'll call it a wrap. Again, thanks, Gareth, for arranging Alex's appearance today. I appreciate that. And we'll continue on and see you all next Thursday afternoon. Have a good week, everybody.
Thank you, Alex, for the presentation.
Sure.
Thank you.
Alex.
73 all.
Right.